Hello everyone, I am Snigdha Kakkad and this is my channel AccelerateAICareers. Today I've brought you a very interesting problem, LeetCode 162, find peak element. This question has been asked by Meta, Amazon, Google, Bloomberg, Microsoft in their last 0 to 3 month of interviews. It's a very important question. Why is it such a famous question and I would say a medium level complexity question is because it's easier to solve this question in O(n) time complexity, but the examiner will expect you to solve it in O of log n time complexity, which adds on to the complexity of the question itself. Now, what does the question say? So you have been given a zero index integer array nums and you have to find the peak element or the inflection point. What is a peak element here? A peak element is such that both of its neighbors, left neighbor and right neighbor, are less than that the peak element itself, and you have to return the index of that number where the peak occurs. So for example, you have been given 3, 2, 1 and now you would say that it monotonically decreasing array. So how come there is a peak here? So in the question you have been given that assume that before the first element occurs, that is index 0, there is minus infinity, and after the last element occurs, there is also minus infinity. So if you assume that, then you would see that 3 has 2 as a neighbor, which is less than 3, and minus infinity, which is again less than 3. So that's why 3 is the peak element and the index would be 0. So you will return 0 here. Now say suppose you have 1, 2, 3, 1 here, which is example 1 itself. So in this case, if you see at index 2, you have an element 3 and its neighbors are 2 and 1, which are both less than it. And you can say that the peak occurs as index equal to 2. If I go through the entire array and then keep on checking its neighbors, I will be able to check both the left and right neighbors and finally get the peak element. Yes, of course, you are right. But the solution will have time complexity of O of n. That's why your brute force approach will not work here. You want a O of log n time complexity and constant space complexity. You can't use some additional data structure. So is there any approach that comes to your mind that can help you solve this question in such time? So yes, there is binary search for log n time complexity. Now you would say, how would binary search be applicable here? Because usually in binary search, we find the middle point between the left pointers and right pointers, and then we rule out one side of it, of the middle point. Either we move the left pointer or the right pointer and narrow down our range of search. But here we cannot narrow down the range of search because suppose you have 1, 2, 3, 1 and you find the middle point. The middle point would be somewhere at index 1, that is 2. If your left pointer is at index 0 and your right pointer is at index 3. So your middle point will land at index 1, that is 2. And 2's left neighbor is 1, which is less than 2, but right neighbor is 3, which is greater than 2. So you would say, which place should I rule out? Should I rule out the left side of 2 or should I rule out the right side of 2? Yeah, that's a question. That's why I would say we are applying a different version of binary search here and not exactly binary search. So to rule out one side, we would look which neighbor is greater than the point at the middle pointer. So right now at index 1, which is your middle pointer, the value is 2. And the value to the right is 3, which is greater than 2. So there is a chance that there is a slanting increase towards the right side. So if it is monotonically increasing, then your peak would be at the rightmost pointer. But if it is not monotonically increasing and it is decreasing at some point and increases to some point and then decreases, then the peak is for sure here. It's not the other side. So you can definitely rule out that side where the neighbor is less than the value at the middle point. That's the refined form of binary search. So if I do that, then at middle point where I have 2 here, I equal to 1, I'll move my left pointer to m plus 1. So if I move my left pointer to m plus 1, that is my left pointer moves to I equal to 2. And my right pointer will be at I equal to 3. So the middle point would be at I equal to 2. Then if middle pointer is at I equal to 2, I'll again check its neighbors. And if the value is 3, the neighbors are 2 and 1, which are both less than it. So hence you have find the peak. Now this is true in the reverse side as well. Say suppose instead of 1 there would have been 3 and instead of 3 there would have been 1. In such a scenario, your middle pointer, which is at I equal to 1 in the beginning, would have 2 and you would check which side has the greater neighbor. So the greater neighbor is on the left side. So you would rule out the right side here and you would go here on the left side. So on the left side, either it would be monotonically increasing this way, that is the array would be monotonically decreasing and you will have the peak element at index 0, or it would be increasing to some point and then deflecting and going low. In such a scenario also, peak would be on the left side. So you can definitely rule out the right side. So that's the refined version of binary search we are going to implement here. But you would ask me, what if my middle point at some point, say suppose I found my middle pointer at value 2 here, and both of its neighbors are same. Say instead of 3, it's also 1. And it's 1, 2, 1, 1. So anytime if this happens, you have already found the peak, because the peak would be 2 then. So that's not possible. So every time you will have different neighbors. If you have the same neighbor, you have found the peak. Now, if you have understood the intuition behind the question, you can solve it very easily. The coding part is not that tough. The part which was tough was figuring out how to apply binary search here. Now let's start coding it. So I'll first initialize my pointers. My left pointer would be at 0. My right pointer would be length of nums minus 1. And now I will write my while loop while left is less than equal to right. And then I will find my middle pointer. Now you can find your middle pointer, of course, by L plus R by 2. But there is a chance that you will run out of bounds and then this will give you errors. So instead of doing that, I'm going to do L plus R minus L. I'll calculate the distance and then do integer division. So this will help you tackle that case when you run out of bounds. So now you have found your middle pointer. Now check for left neighbor. So first of all, check for out of bounds. So if your middle pointer is greater than 0, because if it is at 0, you cannot check for left neighbor, right? And nums m is less than nums m minus 1. That is your left neighbor for the middle pointer value is greater than your middle pointer value. Okay. So in that case, you will move your right pointer to m minus 1 because your left range has a higher neighbor. Else if your m is less than length of nums minus 1, so that it doesn't hit bounds on the right side, and your nums m is less than nums m plus 1, that is your right neighbor is greater. So I will add a comment here, your right neighbor is great. So you are handling the out of bounds case also at the same time and checking for the neighbor. In such a scenario, you will move your left pointer to m plus 1, which we did in our example as well. Now else you have found the peak and then you can return m directly. So this is the entire code. Let me run it. It's accepted. Let's submit. As you can see, our solution beats 100% of the solutions on LeetCode here. So it's definitely a good solution. Let me know if you have a better approach to solve this question. I would be happy to learn from you here. If you like my way of solving problems, subscribe to my channel to get notifications for your daily LeetCode challenge. Thank you.